This conference will now be recorded.
Hello everyone. The topics we are going to discuss today: Ostwald's dilution law, relation between K and Kb, pH indicators and how we use them in titiometry, Ostwald's theory of indicators, selection of pH in titiometry. Ostwald dilution law. So this law basically helps us to understand the relationship between the dissociation constant of weak acid and also weak base with its degree of dissociation, and C. So here we have three quantities. One is Ka or Kb, that is dissociation constant of the weak acid or weak base. Then we have this degree of dissociation alpha. What is alpha? In detail we have seen in the last class, and the concentration of the acid or base. So for example, if I am taking the weak acid, acetic acid, CH3COOH, and when it is dissociated to CH3COO minus anion and H plus. So for this, initially if the concentration is for CH3COOH, if it is C, these two are 0, 0, then alpha is the degree of dissociation. So the remaining concentration at equilibrium, that will be C minus C alpha. So the same thing we have already done in the last class. And as it is 1:1, that means from 1 mole of CH3COOH, you will get 1 mole of CH3COO minus and 1 mole of H plus. So that is why these two are also C alpha and C alpha. Now, if this is so, the relationship of that is Ka, if we write in terms of concentration of these two species, that will be in the numerator, and in the denominator there will be the undissociated remaining amount of CH3COOH. So directly I am writing C alpha for acetate ion, then for H plus also another C alpha, and in the denominator we have C common 1 minus alpha. So CC will be cancelled. Ultimately you are getting C alpha square divided by 1 minus alpha. So this is the relationship between K and C and alpha, but here this 1 minus alpha we will do one approximation. As alpha value is very less, so 1 minus alpha as if it is almost equal to alpha, so almost equal to 1. So if that is the case, then Ka will be equal to C alpha square, because here we have considered 1 minus alpha as if it is almost equal to 1, because alpha is very small value. So Ka is equal to C alpha square. That means alpha is equal to root over Ka divided by C. So here we have total three quantities, right? We have alpha, we have Ka, and we have C. So among these three quantities, if you know two of them, obviously another one we can easily calculate. Similarly, if we consider a base, same thing we can do. So in this case, Kb expression, that will be again equal to C alpha square 1 minus alpha approximation. It will be almost equal to C alpha square. So ultimately alpha is equal to root over Kb divided by C. So this relationship we can reach. Fine. Considering any base, like as we have taken here as example, we have taken acetic acid, you can also take any other base that has to be weak. So this is the ultimate expression we are getting. Okay, now we will try to see how using this type of equation, these two equations, one is for weak acid, another one is for weak base, how we can solve some problem. So here we have this problem, a solution of 0.1 molar of a weak electrolyte is found to be dissociated to the extent of 1.20%. So this is basically the fraction of this weak electrolyte. Acid base, that is not clearly mentioned, and that also we don't need to know. Extent of dissociation is 1.2%. See, this value is so small. This is actually alpha in terms of percentage. And molarity is given. That means this is nothing but C. So you know C, you know alpha. You have to find out dissociation constant. I am writing here K because we do not know whether it is acid or base. So I am not using any subscript A or B. So two values are known, we have to find K. And that we will do in this way. First, this alpha as it is given in terms of percentage, you have to change it to, that is, you have to divide it by 100 because it is given in terms of percentage. So after dividing this value with 100, you are getting 1.2 10 to the power minus 2. Now you have to use this equation, K is equal to alpha square C, the same equation. That is, you can also write it like this. Actually, it is same thing, Ka by C, but better we do not use any subscript because we do not know that is acid or base. So K is equal to alpha square and C. This is the value of alpha, there is square, and C value is 0.1 molar, that is given. So after calculation, the final value, that is the dissociation constant of the acid, that is given. Okay, here acid is mentioned. Fine. So we can write A. So this is the value finally we are getting. So here alpha and C, these two are given, but the value of dissociation constant is not known, which we have to find in this problem. In the next problem, here Kb value of ammonium hydroxide, which is nothing but aqueous solution of ammonia base. So this is the weak electrolyte in this case. Kb value is given. In the previous problem, we have calculated the K value, but now in this problem, Kb value is already given. We have to calculate the percentage of ionization. That means here alpha value we have to find out. That is not given. And C is also there for this solution. So using this value of Ka and C, we can calculate alpha. So this is the relationship, alpha is equal to root over Kb divided by C. Now we know the value of Kb, directly put it here, and the value of C, basically it is 0.06, and it is written in this way so that calculation becomes easier in terms of power of 10. So ultimately the answer of alpha is like this, and 1.732, but after dividing it by 100, that is the value that you are getting when you are dividing it by 100, this 10 to the power minus 2 and these two, it will be cancelled, right? That is, this whole quantity you have to divide. It is 10 to the power minus 2. Or if you simply remove this 10 to the power minus 2, which is basically divided by 100, then also it means same. So in terms of percentage, you have to express it ultimately in terms of percentage. So that is why divided by 100 or multiplied by 10 to the power minus 2, same thing. This part we are omitting. So now it is like the value will be 1.732 percentage. So as it is in terms of percentage, we are removing this 100, which is in the denominator. Here in this problem, so basically Ostwald dilution law, it expresses the relationship between the dissociation constant, the alpha value, and the C value. Now in this problem, after solving it, you will be able to understand how with change in concentration there is effect in the value of K, or sorry, in the value of alpha. That is, you are moving from one concentration to another concentration. What is the effect on alpha? That also you can understand when you will solve this problem. So in this problem, an acid is given where Ka value is 4 into 10 to the power minus 4. You have to calculate the degree of dissociation of this acid at two different concentrations. One concentration is 10 to the power minus 2. Another one is slightly less, actually not slightly, it is 100 times, right? 10 to the power minus 4. So two different concentrations. Suppose this is C1, this is C2. Two different concentrations are given. K value is obviously same because it is the same acid. Same acid, two different concentrations. So you have to calculate the alpha value first for C1 using K, and second for C2 again using K. So then we will look at the value of alpha and we will be able to understand that when you are doing 100 times dilution, what is the effect on alpha? That is, what is the effect on degree of dissociation? That will be clear. So for C1, which is 10 to the power minus 2 molar, alpha value is Ka divided by C. So here we are getting the final value 0.2. And when it is concentration C2, this is C1, this is C2. Now the value using the same expression, we are getting 2. So here you can see it is 0.2, it is 2. So it is 10 times increase, right? That means with dilution, degree of dissociation is increasing. So now we can conclude, when the dilution increases by 100 times from 10 to the power minus 2 to 10 to the minus 4, dilution increases means what? Concentration decreases, because dilution and concentration, these two are inversely related. When you are decreasing the concentration, that means you are diluting it more and more. So it is 100 times dilution, but in terms of concentration, it is from 10 to the minus 2, you are now decreasing it to 100 times less, which is 10 to the minus 4. Now when you are doing so, dissociation is increased by 10. So the conclusion is, it is written in bold, when dilution increases, the degree of dissociation of weak electrolyte also increases. So this is the ultimate statement of this Ostwald dilution law. And this is the statement, but using this expression, that is the relationship between alpha, K or Kb and C, we can solve this type of problem where any of these three unknown quantities are given. So any of these two unknown quantities given, and the third one you can calculate using this expression. So this is the statement of Ostwald dilution law, but remember, it is only for weak electrolyte. It is not applicable for strong electrolyte, because strong electrolyte there is complete ionization, so no question of degree of dissociation, right? Degree of dissociation means what? When there is not complete dissociation, the amount of weak electrolyte that you have taken, some percentage of it, and that percentage is actually alpha. Some percentage is only in dissociated form, not all the molecules are dissociated. But if you take any strong electrolyte, all the molecules are dissociated, so no question of alpha, and Ostwald dilution law obviously not possible for strong electrolyte, right? Now this law is still we are continuing. Why? Because we'll see some more application of this. So until now we have seen that when alpha, K value and C, any two values are given, and the third one we are calculating. Now we will do something new. The concentration of H plus or H3O plus, or you can say hydroxide ion, that is HO minus, that is also possible. That we can calculate using K values as mentioned below. And if it is HO minus, then you have to use Kb value. Remember the expression that is Ka is equal to C alpha square divided by 1 minus alpha. But in this, I'm just going back to the slide. So in this slide, remember, after this, initially C is the number of moles of COH present in 1 liter. These two are 0. But when alpha percentage of C is dissociated, obviously the amount of H plus produced is C alpha. So concentration of H plus, that is actually C alpha, provided volume is 1 liter, right? So if it is the case, then we can also find out the concentration of H plus or HO minus, and that we are going to discuss. So H plus is C alpha. Now in this that is expression, in place of alpha, you can write root over Ka by C, because that is the value of alpha. Now this C, if you bring it inside the root, it will be C square. So one C is cancelled. Ultimately, H plus concentration in terms of C value and Ka is like this. Similarly, for HO minus, you can also do the same thing. It will be C and Kb, right? So here we have this problem. Calculate the pH of 0.1 molar. So this is the value of C. For acetic acid, dissociation constant is given 1.8 10 to the power minus 5. So pH you have to find out. That means first you should know what is H plus. Once you know H plus, then you can put negative log before it, and that is actually pH. But you have to know first what is H plus. And for that, you can use this equation that we have just seen. So pH for weak acid, if we want to calculate first H plus concentration, which is root over Ka into C. Now Ka value is given 1.8 10 to the minus 5 and C is 0.1. So this is the ultimate answer for H plus. But we need to know pH value. So pH is negative logarithm of H plus. So put negative log before this value, that is H plus, and it is basically negative negative cancel. So 3 minus log 1.34. So ultimately we are getting the pH 2.87. It will be obviously lesser than 7 because it is acidic solution. So just check once that you are getting it. So it will also prove that your calculations are right. That is, it is less than 7. It is acidic, not neutral or basic. So here we have learned that H plus concentration we can calculate. Similarly, if H plus is given, you can also calculate C. Suppose K is given, H plus is given. So use this equation, you can calculate C. And another possibility is if pH is given. So if pH is given, basically it is H plus concentration given. So using this expression, if pH is given, you can calculate H plus, which is 10 to the power minus pH. Whatever is the value of pH, that is actually, if you put it like this, it will be H plus. So in this way, if pH is given and Ka is given, you can also calculate C1, right? Here we have the problem pH of a 0.1 molar solution of the acid. Suppose the acid is HQ. So pH value is 3. Molarity is given. That means C value is given. So you know H plus, you know C. What you have to calculate? You have to calculate ionization constant K of this acid. So remember the expression pH is given. So from pH you can calculate the value of H plus concentration. So HQ it will dissociate as H plus and Q minus, and H plus is 10 to the minus pH, that is 10 to the minus 3. Okay, and C value is given. So once you know H plus and C, using the expression that is H plus is root over K into C. Now in place of H plus you will put it, you will put the value which we have already calculated, and C is directly given in the question. So we can calculate K value, which is minus 5. So this should be the correct answer. 0.01 molar acetic acid solution, 1% ionized. So this is actually alpha. It is given in terms of percentage, but actually the value will be 0.01. You just have to divide it by 100. 1 by 100, 0.01. pH of this solution you have to find. Here alpha value given, C value given. You know C, you know alpha. You have to find out pH. That means first you have to find out what is H plus, right? So H plus is basically C into alpha. So C you know 0.01, alpha is simply 1%. In terms of percentage it is 1. So you have to divide it by 100 or 10 to the power minus 2. So it is 10 to the power minus 4. pH is negative logarithm of H plus. So ultimately the pH value is 4. Again just check it. Obviously all the options it is less than 7, so no question of checking. It is option D, that is the correct answer. Percentage of pyridine. So pyridine is weak base, though it is that is organic base, but it is example of weak base. This is the formula. C5H5N. So if you treat it with water, it will take 1 proton. Now nitrogen is positively charged and you will get HO minus. That is the same type of expression. In general, if I write it will be like this. Will you be understand? So as if BH plus you can compare with this species and HO minus. So here B is basically pyridine. Percentage of pyridine that forms pyridinium ion. So pyridinium ion is basically this one. Percentage of pyridinium. That means initially here it is 0.1 molar. That means 0.1 mole present in 1 liter. So this is the initial concentration, but only the percentage that is dissociated, that percentage you have to calculate, because here how it is mentioned, percentage of pyridine that forms pyridinium ion. That means from this species to this, or from B to BH plus, this percentage, which is nothing but alpha. It is basically asking the value of alpha. C is given, Kb value given for this base, which is 1.7 10 to the power minus 9. So only alpha is unknown. So this is the same equation that we have already written. Kb value is alpha square C divided by 1 minus alpha, right? But as we do the approximation, because 1 by alpha it is almost equal to 1, so ultimately it simplifies to like this. So alpha is root over Kb by C. Kb value 1.7 10 to the power minus 9, and it is 10 to the power minus 1. So ultimately it will be root over 1.7 10 to the power minus 8. Okay, so from minus 8, do the calculation individually. From this you will get 10 to the power minus 4 and root over 1.7. So ultimately you will get the value 0.013. That is in terms of percentage. First you will get it as if it is 1.3, but as it is in terms of percentage, you have to divide it by 100, and then only you will get it is in terms of 0.01, like this. Okay, this is the correct answer. So this chapter, that is problems from this chapter, is very common. So we'll try to solve problems as many as possible. Right? Consider the following statements. Total 4 statements are given. Correct statements are: option 1 is saying that only A and B, then A, B, C, then A, B, D, and last option it is saying only B and C. So one by one we will see. The first statement is saying pH of a mixture containing 400 ml of 0.1 molar H2SO4 and 400 ml of 0.1 molar NaOH, that is 1.3. So first write the equation. H2SO4, it will react with 2 moles. Why 2 moles? Because in this case 2 replaceable hydrogens are there, and you are getting Na2SO4. Basically it is not equilibrium sign, because the reaction will happen, it will be completely, all the molecules will react with each other. So it is not that it will be incomplete, there will be equilibrium. Actually it will be fully converted to the product side. So Na2SO4 and 2 molecules of H2O. Here the important point that you have to notice, the 1 mole of H2SO4 reacting with 2 moles. That means 400 ml, and this is molarity. So when you have volume in ml unit and concentration in molarity, directly if you multiply, you get the value 40 millimole. Similarly, here initial amount is 40 millimole for both, because this is also 400 0.1 molar. But as it is 1:2 reaction, so limiting reagent, that will be this one. So all the NaOH that will be consumed. So if 40 millimole of NaOH consumed, obviously only 20 millimole of H2SO4 will be there. So NaOH will be fully converted to Na2SO4 and 20 millimole will be remaining. Okay. So if 20 millimole is remaining and total volume is 800 ml. Right. Now, when you are multiplying volume in ml and molarity, you are getting number of millimoles. Similarly, number of millimoles if you divide by volume 800 ml, then you will get the corresponding molarity. So the molarity is 1 divided by, one correction I have to make, 20 millimole, that is H2SO4 left. But if from 1 mole of H2SO4, basically we get 2 moles of H plus, or if you write in terms of millimole, I can say from 1 millimole of H2SO4 you get 2 millimoles of H plus. So when you are trying to know the concentration of H plus, then number of millimoles of H2SO4 you have to make it double. So in terms of H plus, it is basically 40 millimole. So when we want to know the molarity for H plus, now we have to write 40 here. So that is why it will be now 1 by 20, that is the molarity of H plus. So this is the concentration of H plus. So why I am calculating concentration of H plus? Because ultimately we have to check whether this statement is correct or not. It is saying that pH of this mixture is 1.3, right? So here all NaOH consumed, H2SO4 extra left, that means the solution will be acidic. So it is obviously less than 7. But acidic, what will be the pH? That we have to find. And pH find means H plus concentration you have to know. So in this way we have calculated H plus concentration, which is 1 by 20. So ultimately pH value, that will be negative logarithm of H plus, which is 1 by 20 or 0.05, and that value is 1.3. So this statement is basically correct statement. Okay, no problem. So let me resolve this. Now we have to see second statement. So if it is correct, obviously option 4 where A is not mentioned, option 4 is not correct. Second statement is saying ionic product of water is temperature dependent. So Kw value, remember we have seen in the last class that with increase in temperature how it is changing. It is basically increasing because the H2O, when it is dissociated to H plus and HO minus, that process is endothermic. So with increase in temperature, Kw value, ionic product, that increases. So it is temperature dependent. So this statement is true. This is also true. So A and B, these two are true. But A and B present in all these options. So still we have to consider C and D. C is saying monobasic acid, K value given, pH is also given. Degree of dissociation, it is mentioned 50%. That means alpha value is 0.5. Just divided by 100, it will be 0.5. But is it true? That we have to check. So we know that pH given means what? pH given means H plus concentration that is given, which is 10 to the power minus pH, that means 10 to the power 5. So you know H plus, that is known. You also know the value of Ka. So when these two are known, we have to find alpha. Which equation we have to take the help of? It is basically this equation. Remember, K is equal to C alpha square 1 minus alpha. This equation we have to take the help. Now don't use another equation which is K alpha equal to root over Ka by C. Don't use this equation. Why? Because here alpha we have to find, that is okay. K is given, but C is not given. Here H plus is given, not C given. So that is why we cannot use this equation. We have to use this equation. So in this equation, write it in this way, as if you are writing C alpha square in this form. C alpha dot alpha. Why I am doing so? There is a reason behind it. So I am doing so because I will replace this C alpha with H plus concentration. Remember, H plus concentration is basically equal to C alpha. So in this place, now I will write 10 to the power minus 5 multiplied by alpha. And this value is also 10 to the power minus 5. So both sides, these two cancelled. So now we are remaining with 1 minus alpha equal to alpha. That means 2 alpha is equal to 1. So alpha is 1 by 2, which is 0.5. If you divide it by 100, sorry, multiplied by 100, it will be 50, in terms of percentage, it is 50%. That means this statement is also correct statement. And what about the last statement, ABC? Now ABC correct means you can choose option 2 because you don't have to move to D. So just to save time, once we are confirmed that A, B, C, these three are correct, obviously option 2 we can easily choose. So this option is not correct, but why D is not correct, that you will also check. It is saying that Le-Chatelier principle is not applicable to common ion effect. Now Le-Chatelier principle that we have already finished, but in this case common ion effect you can consider. Suppose you have taken any acid He and it is dissociated as H plus and A minus. Now in this solution of HA, if there is already some ion A minus is present, but A minus is also coming from the acid that you have taken, that means there will be some common ion of HA. Now from Le-Chatelier principle, what we know? We know that when you are moving from left to right, this species, if it is already present in the medium, that means its concentration is already high, then the system will try to move to counter effect this, and as a result the dissociation will be decreased because A minus is already present from some other source. So the tendency of H plus to move towards right hand side, that tendency will decrease. So it will be, that is, this is a common ion because A minus is already present. It is also true for H plus. Suppose already H plus is present in the medium, so obviously it will affect HA dissociation. You can compare with another, suppose another system you have taken only HA in water and where there is no common ion present initially. So here the dissociation, and other system where already some H plus present or A minus present, there the dissociation of HA, obviously these two dissociation are not same. So this is because of Le-Chatelier, and we cannot say that it is not applicable to common ion effect. It is obviously because of this common ion effect, the dissociation is becoming less, and that is why it is because of Le-Chatelier principle. So we cannot say that it is not applicable. This is false. So D is not correct. A, B, C correct. Option 2 correct option. Fine. Relationship between Ka and Kb. So individually we have seen Ka and Kb, and there is a basically K and Kb, you can relate it to Kw also. So now the equation that we are going to derive from that equation will be relation between not just K and Kb, it is also relationship with Kw. There is a simple relationship between the magnitude of Ka of an acid. Suppose the acid is Ha. If you actual example, if you want, you can consider as if it is HCN, hydrocyanic acid, and the corresponding conjugate base A minus. That means if it is hydrocyanic acid, corresponding conjugate base will be Cn negative. So Ha, it is the acid, and for this obviously there will be some Ka value, and its conjugate base A minus, because it is base, so there will be some Kb value. So this will be the two equations. Ha, when you have taken it in water, it will be forming H2O plus and the conjugate base A minus. Now this conjugate base, when it will be in presence of H2O, it can also again form Ha. That is, it will take proton from water, it will form Ha, and HO minus hydroxide ion will be produced. So treat it as if it is a base, and the base is taking a proton from water. So for the first equation, we can write the Ka expression. For the second equation, we can write the Kb expression. Now the interesting thing is, when you are adding these two equations, some ions will be cancelled from both sides. See, this will be cancelled, right? Then Ha, these two will also be cancelled. So now we are remaining with two H2O, one hydronium, one HO minus. So this is the final equation after you have added these two equations, number 1, number 2. But look at this equation. This is nothing but autoionization of water. And the dissociation constant for this particular equation, that is nothing but Kw. Kw you can also write in terms of like this. That is also you can do. Both are fine actually. This is also okay. So whether you take 2H2 or 1, both are fine. So here we have taken 2H2 because from when you are adding this, you are getting. Now what I will do, I will write the expression for Ka. K is concentration of H2O plus. Just look at the equation. Concentration of A minus divided by Ha undissociated. I will not write H2 because it is present in excess. Similarly, for Kb, this is equal to Ha right hand side and HO minus divided by A minus. I will not write H2. Now, if you multiply Ka and Kb, some terms will be cancelled. Which term? Ha will be cancelled, right? So ultimately, Ha will be cancelled, A minus that will also be cancelled. So ultimately, you are left with H3O plus multiplied by HO minus. Now this is nothing but the expression of this, right? Because Kw is concentration of H2O plus, concentration of HO minus, water is not considered. So ultimately we can write Ka into Kb, that is equal to Kw. This is the relationship. Now if you take negative log both sides, it will be negative log Kb plus negative log A B negative log Kw. Now negative log something means we can write it in terms of pKa, pKb. This is pKw. Okay. Now if that is the case, here. So this expression we are getting, right? So pKa, pKb, one mistake I have made. So I will take negative log for these two expressions, not K and Kb. So what I will do, just focus on this part. K and Kb equal to Kw, that is fine. So this expression, remember. Another one, if I take negative log for H3O plus, then it is in multiplication form, right? So when I'm taking log, it will be plus. Now negative log H2O plus is nothing but pH. Then negative log HO minus is actually POH. And negative log Kw is pKw. Now at 25 degrees centigrade, the value is, that is Kw is 10 to the minus 14. That means this value is 14. So pH plus, but this is only at 25 degrees centigrade, accurate value if we say. So this is another important relationship. So not just relationship between K and Kb like this. Another relationship also we are getting, which will, that is for solving problem, it will help us. And that is pH plus POH is equal to 14. But remember, this is at 25 degrees centigrade. Okay. So from this, one conclusion we can draw. That higher is the value of Ka, smaller is the value of Kb. Now why we are saying so? Larger the value of Ka, smaller is the value of Kb, because the product of these two is fixed, right? So when product of these two is fixed, obviously Kw is fixed. So when you are increasing the value of Ka, Kb value, that will obviously decrease. So it means what? Ka and Kb, we have already considered it is the dissociation constant of the acid H. And Kb, it is the dissociation constant for its conjugate base. So when base is, that is stronger is the acid. Stronger acid means Ka is high. Weaker will be its conjugate base. Now Ka when high, Kb is low. It means what? Its conjugate base, that will be weaker. So this conclusion we already have seen previously, but now you can also prove it from this relationship, because the product of these two is fixed. So for Ka, if when it is increasing, that is if it is having very high value, obviously Kb will be low. So that is why we can draw the conclusions. The stronger is the acid, weaker will be its conjugate base. So in this case, acid we have taken Ha, or you can consider as if it is HCN. Conjugate base is Cn minus. So Cn minus, it is very weak base. Okay. And remember, same conclusion you can also draw. That is, if acid HCN, it is weaker. That means if Ka value is very low, obviously Kb value will be high. The reverse statement is also true. pH indicators. So to understand the pH value, especially these indicators that we are going to discuss in detail, that will be for specific purpose, and that is in tritimetry, where we take some acid and base and we do neutralization reaction. And the purpose for doing titration is that when you have acid or base you have taken, suppose you know the volume of both and concentration of only one species, so you will be able to calculate the concentration of the unknown acid or base. So that is the purpose of doing titration. And in this titration, indicators, pH indicators, they have a significant role. Okay, but before understanding that role, we have to understand what is pH indicator. Okay, the substance which change to specific colors in different pH. So these indicators are a species which will have different color in different pH range. So suppose when it is acidic range, that is below 7, it will have a particular color. Suppose I am saying yellow. When it is in basic range, that is greater than 7, 7, 8, 9, 10, 11, whatever, then it will have another value. So these two different values, one is in the acidic medium, another one is in the basic medium. So this type of specific property you can find for them. So the substance which can change to specific color in different pH range. It is not that at pH 2 it is one color, pH 3 is one color. We do not do in that way. So that is, it is saying pH range. So normally how we mention the color, whether it is in, what is the color in acidic range, what is the color in basic range. These two range specifically we consider. So whatever indicator we will mention, it will be, there two colors will be mentioned. One is in the acidic medium, acidic pH range, another one is the basic pH range. So they are called as pH indicators because they are indicating whether the medium is acidic or basic. Now in acid-base titration, where we are going to use these species, in acid-base titration what we do, the concentration of an acid or base is determined. How? By exactly neutralizing it with a standard solution of base or acid, having known concentration. So for example, suppose I am saying I have taken NaOH and I am mixing with it HCl. Now both, if it can happen that NaOH you have taken in conic, mostly acid we take in conical and base we take in burette. So NaOH you have taken in burette and here we have conical, where we have taken the acid HCl, and here we have NaOH, right? So here acid solution, the volume is known, its concentration both are known. right? Now NaOH from burette reading, you will be able to know the volume, but suppose concentration is not. So among this volume and concentration for both species, 3 will be known. So if it is so, you can easily calculate the concentration of the unknown species. It may be also for HCl, that is volume and concentration for NaOH known, volume for HCl known, but C is not known. That may also happen. So that is mentioned here that we do in titration, acid-base titration. There are different types of titration. Acid-base titration is one of the type. So concentration of acid or base is determined, and that is done by neutralization reaction, because acid-base reaction is neutralization reaction, where salt is formed, water is formed. And in this case, we use these indicators. Now, these indicators, what is their nature? What is their chemical nature? They are actually weak organic acid or base. If you look at their structure, though they are having very large structure, we are not going into the details of structure. I'm just saying that they are having very large complex structure. So they are organic acid or organic base, and obviously they are weak organic acid and bases. Fine. So such compounds are useful as indicators in acid-base titration and finding out H plus concentration. It may be HO minus also. An indicator undergoes color change at the end point of titration. So end point of titration means what? Initially, suppose you have taken HCl and NaOH amount you have not added at all. Now, some indicators, suppose 2 to 3 drops, it is already present here, and it is showing some specific color in the acidic medium. Now you are adding NaOH. So first the medium is acidic in nature. Gradually you are adding NaOH, but still it is acidic. Once the neutral point is reached, okay, once the neutral point is reached, now the reaction is complete, right? So we basically know that burette reading. So initially if the burette is here, once this neutralization point is reached, suppose now it is here, but how you will understand that the neutralization point is reached? That you will understand from this indicator color change. So suppose first it is in the range 1 up to 7, any value, then this is the neutral point where reaction is complete. Acid is consumed by NaOH, HCl is consumed by NaOH completely. Now once you are moving towards this side, that is the basic range, there will be, that is 1 drop extra of NaOH, it will now show different color. So in this acidic range there is one color. Suppose I am saying this is red, and once it has crossed this 7, it has different color. So now it will be, there is 1 drop extra of NaOH or any base. Basically these two examples though I have taken for simplicity, but when it is strong acid and strong base, there is no such suitable color, right? So better I mention it some other base which is weak base, suppose NH4OH, then it will be better. Okay, so why that is strong acid, strong base, this example I do not want to take, that you will understand later. That is when we will discuss indicators for different types of acid base combination, then you will be able to understand. So here basically we have taken weak base NH4OH and strong acid HCl. So in this case, once it has crossed this neutral point, now it is in basic range. 1 drop of extra base, it will be in basic range, and in basic range it will show different color. So that means now, though it is 1 drop extra, but that will not matter. Just extra 1 drop, it will show a drastic color change, and then you will stop it. And in this way you can understand that neutral point is reached, though it is slight excess of base, but that doesn't matter, it will not create any problem. So in this way indicators undergoes color change at the end point of titration, and we will be able to understand that neutralization point is reached. So see here we have written indicator with direct structure we will not take because it is having very large structure. So it is written in simple as if it is written in HIN. In means indicator, and it is attached with some H. You see the acid form. Now in water medium, suppose there is an acid base, simply you have taken the indicator which is in HIN form. Now once it is taking a proton from water, it is weak acid or base. It is taking a proton from water. it is converted to H3O plus, and this is the corresponding conjugate base. So it has donated one proton, so that is why it is acid form, and the conjugate base form is In minus. Okay, so one form is acid form, another form is conjugate base form. It will have different color in these two form. One color from in HIN form, another color in In minus form, right? This color change is because of ionization of acid base indicators. So here we have this general formula for indicator. Different due to ionization of the acid base indicators as the unionized form. Color change is due to ionization of acid base indicator as the unionized form has different color than the ionized form. So another way you can say that in HIN form it is one color, having one color, in IN minus form it is having another color, and that is mentioned here. So that is because of this particular property of these species, which we are mentioning as pH indicator, as they are showing this specific property, that is the reason we can use them as indicator in acid-base titration. Otherwise, we will not be able to take them. Because of this particular property, it is helping us to understand the neutralization point when we are doing some acid-base titration, right? So Ostwald theory of indicators, if we start it, we will not be able to finish it. So Ostwald theory is basically saying how this indicator, what is the mechanism of this indicator, that is how they are changing color into different form. So in detail we can understand from this thing, right? So we'll discuss it in the next class. Today we are ending here. Thank you for listening.